So I hope my screen is visible in PPT mode.
Yes,
Yes,
ma'am,
ma'am,
it's
it
visible.
is.
Is the content double pipe heat exchanger?
Yeah.
Um, so good morning to all of you, and this is the second class of the course CED 2, and in the first class uh, we have introduced the subject, and we have discussed that how this subject will be beneficial for you, or what type of skills you will have once you will read this particular course. And then we have discussed the equipment which we are going to cover over here, and meaning of designing and all. And then we have started classification of heat exchangers. Though we need to design only shell and tube heat exchanger, but some prelim information is required. It's important for you to understand, and this type of information are very useful when you appear in interviews for any chemical process. Okay, so therefore that could be consolidated information with you regarding the heat exchanger, its working, and its category and all. Okay, so some of the heat exchangers in from that classification I will cover in detail, and then we will focus on the design parameters, and then we will start design of shell and tube heat exchanger. So uh, when we consider heat exchanger, the very common heat exchanger comes to our mind is double pipe heat exchanger, and probably at your I think second year or third year you must have done experiment in this double pipe heat exchanger also. So when we consider this double pipe, as the name says, uh, we have two pipes, but two pipes are not separate two pipes. Two pipes are inserted one over another. Okay, so this is the simplest kind of heat exchanger device we could have, and there is only two pipe. When we see the two pipes, and these are if you look at the assembly, these are concentric pipes. Okay, one of a smaller diameter over which larger diameter pipe is simply placed. Okay, keeping equal space at annular side throughout the length. Okay, so when we consider fabrication, that would be fabrication is very easy, manufacturing is very easy, and when we, as I have told you, the name says it is two pipes which are concentric, and one fluid flows inside the inner pipe while second fluid flows at annular space between two pipes. As that is very simple unit, so it the installation, when we consider manufacturing, when we consider maintenance, when we consider all these are very what we can say, that will be supported by very less uh, what economics. Okay, so costing is very less in that. So we should consider that, okay, if costing is very easy, every time we should use that. Okay, because maintenance and everything is so easy over here, fabrication, along with the economics, which is major concern of the industry. Okay, so we will see that why this type of heat exchangers are not used very frequently, apart from all these advantages. Okay, but before that, we will see the assembly of double pipe heat exchanger. So if you see this, double pipe heat exchanger, we have two spaces. One is the inner pipe, inside the inner pipe, and second is the outside the inner pipe and inside the outer pipe. Okay, that is nothing but this annular space, and one fluid flows inside this that inside the inner pipe, and second fluid flows in annular space, as you can see over here. Okay, so when we consider a double pipe heat exchanger, usually the experimental what you have performed in heat transfer lab, or that heat exchanger, double pipe heat exchanger is at most it is from here to here. Okay, only one part. Okay, or we can say only this straight part you must have seen. Okay, and if you visualize the double pipe, it is usually a straight pipe, okay, as you can see over here. And wherever I'm having the heat exchange, possibility to exchange heat, like here, like here, like here, everywhere the tube or the pipe is straight. Okay, so heat transfer occurs in a straight pipe in double pipe assembly, right? If you observe like double pipe heat exchanger, and whatever heat transfer area you are having, okay, that heat transfer area will give you this length, right? Heat transfer area, uh, Q is equal to UA delta TLM. So once I'm having the heat duty, once I'm having the like U and delta T mean, you can calculate heat transfer area. There is no problem. But for a given heat transfer area, every time if I consider double pipe heat exchanger as straight, like, right, like if I ask you that this part as well as this part will be added over here in series. Okay, oh, this is also you can consider as the like it is connected, but if it will be connected from here and moves straight, okay, third part will come over here then moves straight. In that way, when I say, then how much space it will occupy over the floor. Okay, because any equipment needs some floor area as well. Okay, so, double pipe heat exchanger, when we keep on considering the straight pipe and only one, what we can say, only one straight pipe, if I want to consider, then the floor area requirement would be very high. Okay. In that case, what could be the possibility that to reduce the floor space, we can make this type of assembly, that in a serpentine way we can we can consider the double pipe, where this straight pipe will appear multiple times. Okay, uh, what we can say, equal length of straight pipe will appear multiple times, just one over another, as you can see over here. So when we see this double pipe heat exchanger, after this it will be bended. The bending will occur over here, and then we will have the straight pipe again, where the heat exchange will be involved. Now the point is, uh, this is the bend, right? And bending is done only in the inner pipe, not the whole shell and tube heat exchanger, like this. Okay, like this. Okay, the shell side, this outer pipe is what we can say, it ended over here and then it starts from here. But this bend is only done with the inner pipe. The reason could be the because bending of two pipe, okay, bending of two concentric pipe, it is very difficult. Okay, and in that way, some way it will be like the inner area will not be uniform throughout, especially in the bending case, but that will be very easy to maintain at a straight case. Okay, so bending will be done only with the inner pipe, but the heat transfer wherever it will be done, there we will have the there we will have two different pipes, okay, of different diameter. So if you see this bending, this we call as hairpin. Okay, this is one hairpin. If I consider the whole assembly, there I am having two hairpins. Hairpins you must have seen, no? That is a simply U type of structure. Okay, U type with arms, with long arms. Okay, so that is that we consider as the hairpin, which usually used by women to make different hairstyles. Okay, so this we consider as the hairpin, this we consider as hairpin. Okay, so if I'm using multiple hairpins, it means double pipe heat exchanger will be divided in uh, regular sizes, and those sizes will be placed one over another. Okay, as you can see over here. So here uh, uh, if in this way we can make the double pipe heat exchanger, we can accommodate more heat transfer area considering less floor area. Okay, I hope you are getting my point. So usually double pipe heat exchanger which are used in the industry, this is of those heat exchangers are of this type only with multiple hairpins. Okay, just industrial heat exchanger I am showing over here. If you count these are the hairpin. So here 1, 2, 3, 4, 5, 6, 7, 8. 8 here and 8 here. Oh, this is basically 16 hairpins. Okay. So, and if you observe the floor area, that is very less. Okay. So, the limitation of double pipe heat exchanger to occupy more area, some way it can be compensated over here. Okay. However, even if I'm considering multiple hairpins, okay, we could have the limitation to use that double pipe heat exchanger, and that limitation is that double pipe heat exchanger are used for small capacity application such as 50 meter square if the heat transfer area we are considering. Okay, so double pipe heat exchanger will be used up to 50 meter square, and beyond that we consider the other heat exchanger which will occupy more heat transfer area in less what we can say in less volume. Okay, or less floor area you can say. Okay, so that is the what we can say the major guideline for this, that you should all remember that 50 meter square and less than that we should consider double pipe heat exchanger, otherwise we should choose shell and tube heat exchanger and others. Okay, further, this configuration is more suitable where one or both of the fluids are at very high pressure, because contamination is in a small pipe, small diameter pipe or tubing is less costly than contamination in large diameter shell. Okay, so in that case, if one fluid is of very high pressure, or we can say one fluid has more fouling tendency, it should be allocated to tube side, inner side. Okay, not the annular side. Secondly, the very important point over here is very high pressure. So if I'm having high pressure, then what will happen? If you consider the go back to the previous course, CED1. Okay, there what we have considered, the thickness we have considered for pressure vessel, right? So the expression was expression like for that we have discussed as P D naught by 2 Fj plus P. Remember? So that diameter, when we are considering there, that diameter is highly dependent, sorry, not diameter, that thickness is highly dependent on pressure. Okay, P D naught by 2 Fj plus P. Okay, so the point is, as pressure will increase, thickness will increase. Okay, and when I'm considering diameter also, like it is P D naught. So D naught, if I'm considering for inner pipe, okay, it would be less thickness in comparison to outer pipe. Okay, So very high pressure, when I'm considering, it is better to use this type of heat exchangers, because uh, if you compare the overall dimension, overall diameter, or we can say the outer diameter of double pipe heat exchanger and shell and tube heat exchanger, for shell and tube it is very high in comparison to double pipe. Okay, so very high pressure, if you consider with either inner pipe diameter or outer pipe diameter, whatever, in double pipe heat exchanger, the thickness will be less, and thickness will be less means you need to include less material, you need to invest less. Okay, so double pipe heat exchanger, where you should use, firstly, the area should be less than 50 meters square. Secondly, the pressure should be very high. Okay, otherwise we will go for what we can say, shell and tube heat exchanger and all. So I hope you understand this double pipe double pipe heat exchanger functioning as well as limitation. Okay, that limitation we can overcome over here with shell and tube heat exchanger. So when I'm considering shell and tube heat exchanger, wherever you will go in chemical plant, at least you will find this heat exchanger. Okay, so this is most commonly used type of heat transfer equipment in chemical plant, especially in refineries, where we can say that is the their all chemical related activities you can observe there. Okay, so when we consider shell and tube heat exchanger, it consists of bundle of tubes, okay, enclosed in a cylindrical shell. So we can have one shell, however, we can have multiple tubes. Okay, so all tubes are placed in a bundle, and that bundle is inserted in the shell. I will show you when we will discuss the design of this. I will show you that how these bundle and shell, all these will be look like, uh, though you already have the idea, but we will discuss that also further. The end of the tubes are fitted with the tube sheet which separate the shell side and tube side fluid. Baffles are used to direct the fluid, and we have the support, the support the tubes. Okay, assembly of the baffles and tube is held together by a support rod. Okay, actually support rod and spacers, all these we will discuss through this diagram. Okay, now we have seen that these tube sheet, if you see, this is the tube sheet. Okay, this is the tube sheet, and these tube sheets are used to insert the tubes, or we can say hold the tubes. Okay, so tube will be inserted over here, tube will be inserted over here, in between it will remain hanging, right? So when we consider this tube sheet, the primary purpose is to hold the tube, okay, because tube will be inserted in this. Second purpose is it separates the fluid of shell side and tube side. Let's say this is the shell, okay? The blue section is the shell, and this is the tube sheet, and this is the tube sheet. So what will happen? Shell, whatever fluid is entering into shell, it will stop over here. It cannot move to this side, okay? Similarly, the fluid cannot move to this side, okay? Secondly, when I'm considering the tube, if you see, this is the inlet of the tube where I'm having the openings, and this will be inserted in these tubes, okay, and exits from here. It means tube fluid will not have any chance to enter into shell side, and shell side fluid will not enter into tube side, and that happens because of this tube sheet. This is one point. Another point, if you see the last slide, another point that was there, we consider these baffles. Okay, so these are the baffles, and if you see the baffles and tube sheet, okay, this is the baffle and this is tube sheet. Okay, one purpose of the baffle is to direct the fluid flow. Okay, because fluid, when it enters over here, it will it cannot move to this direction from here directly. It has to move, it has to follow this path, and then it returns back, and then in that way. So in that way, some wavy kind of fluid pattern you can observe in shell side, and that will happen only because of the baffle. This is one purpose. Second purpose is the baffle holds the tube in between. Okay, otherwise this is one tube sheet, this is another tube sheet, and in between if we will leave the tube hanging, then what will happen when I'm considering high velocity in the tube side? Because of that high velocity, or let's say if I'm having some what we can say lag in flow, okay, so it will give what vibration in tubes. Okay, it will give vibration in tubes, and because of that vibration, tube may coincide from each other. Like this tube may may coincide with this tube may coincide with this. Coincide means they can strike each other. Okay, in the shell side, tube side flow will not have any problem. Okay, it will keep on flowing, but because of vibration, the what we can say, a tube may strike in shell side, so it will create sound, it will create problem in the fluid which is available in shell side to move properly, right? So in that way we can consider the that the regular spacing will be required between the tubes, and that will happen with these baffles. Okay, I hope you are able to understand all points which I am considering. Okay, so in that way you can see the purpose of baffle is to direct the fluid in shell side and to hold the tubes. Okay, and when you observe the baffle as well as tube sheet, wherever I'm having the holes in tube sheet, in the same pattern I'm having the hole in baffles. Otherwise, tube will not will not enter finely or nicely. Okay, I hope you are getting my point. So the type of holes or type of interval in holes we are considering in tubes, in tube sheet, the same I should consider in baffle. The only difference is baffle is only up to here, however tube sheet is throughout the diameter of the shell. Okay, right. So this is another point. Like one was about the tube sheet, second is the tube, second is this baffle, and whole assembly of this baffle as well as tube, that will be supported by support rod. Okay, or that support rod we can I will show you when we will discuss the design in detail. Okay, in this image it is not properly shown, or you cannot visualize over here, but I'll let you know that. Okay, and another point is when I'm using the baffle, okay, how this baffle will take its place. Okay, when I'm having this tube, okay, uh, beyond some tie rods, okay, and tie rods are placed over here. Okay, where I'm not having the tubes. Okay, one tie rod will be here, another tie rod will be here. So tie rod will be placed in the tube side, in the tube sheet, sorry. Okay, and in that tie rod we put the spacer is basically the hollow cylinder. Okay, hollow cylinder which is having larger diameter than the tube, then the tie rod, so that it can be properly inserted. Okay, so the spacer, the purpose of a spacer is like it will cover only this much distance. Okay, uh, and once I'm having this much distance, if I place the baffle, okay, it will take its position up to here. Beyond that it cannot move. Okay, this is one thing. Another thing is, if I need to place this baffle, again I need to put the spacer up from this to this distance, and that spacer will decide the location of this. Okay, similarly from this side, from this baffle to this baffle, again we need to insert the spacer. Okay, so spacers are used to have uniform distance between two baffles. Okay, so in that way you can have the regular placement of baffles in the heat exchanger. Okay, so these are some of the points. And the tubes in form of the bundle may be permanently positioned inside the shell, fixed tube sheet, or that may be removable for ease of cleaning and replacement, that is floating head or U-tube exchanger. Okay, so if you consider this type of tube sheet, this is simply welded over here. Okay, this is simply welded with the shell. It means these tube sheets are fixed. You cannot change that. Okay, so the purpose is uh, it basically holds the tube and further any variation is not involved. If you need to remove this bundle completely, you need to consider the tube sheet removable. Okay, then it cannot be welded over here. It can be fixed over here with nut and all. Okay, nut and bolt, it will be fixed. Okay, so that we call as floating head or U-tube, otherwise it is fixed tube sheet. Okay, just please hold for 1 minute. I will continue. Please wait. Okay. So in that way, you can understand the functioning of shell and tube heat exchanger, and that we will discuss in detail in design of it. Okay, but some of the points you should understand about that we have already covered over here. Just a moment, I will start. Okay. Okay, so next heat exchanger we have is a plate type heat exchanger, and as we have shell and tube heat exchanger and double pipe heat exchanger, those fall in the category of tubular heat exchanger. Okay, and this plate type heat exchanger, you can understand we have the plate as a heat trans what we can say as a separating wall, as we have tube in silent tube heat exchanger. Okay, so this type of heat exchanger includes a series of rectangular parallel plates held firmly together between substantial head frame. So if you see here, I'm having the particular frame. So this is one board where we have all nut and bolts through which these plates are attached. So this is one what we can say metal plate. Another thing is this is the rod. Okay, you can see over at the top, this is the rod, and here again we have the rod at the bottom, which is attached with this assembly as well as this board. Okay, metal board. Okay, so here I'm having multiple, or we can say the uh, plates. We have multiple plates, rectangular plates, which are attached to each other, and all these are basically what we can say movable over this rod and over this rod. Okay, so we can say this rod and bolt assembly as a frame, and over which plates are movable. Okay, so plates have corner ports and are sealed and spaced by rubber gaskets around the ports and along the plate edges. Okay, now if you consider this particular plate, for example, this particular plate, or let's discuss with this first plate. If you see, this first plate has four corners. Okay, here I'm having four corners, 1, 2, 3 and 4, and all plates have the all four corners in the same line, or we can say all these four corners are aligned to each other. Okay, so uh, here I'm having these four corners, and the if you see these black lines, okay, more in a better way we can observe over here. Here I'm having the black lines like this. Okay, so this black line is nothing but the gasket. Okay, another black line is available over here, which moves from here to here and then moves from here to here. Okay, so if you observe this particular plate, okay, uh, here I'm having the black line like this. Okay, and the complete color over here you can see as blue. Okay, you can see red color over here, which is in this port and this port. Okay, and similarly if you observe this plate, here I am having the black line like this, or we can have the gasket like this, and the color mostly over here you can see as red. Okay, so from here you can observe that when like four ports are there, two parallel float, what we can say, two ports of one side are allocated for cold fluid, and two port on another side are allocated to hot fluids. Okay, so in that case, if I'm having gasket like this, okay, it means this gasket works as a sealing to flow, or to avoid the flow of hot fluid in this. Okay, so hot fluid will come over here and it will spread over the plate and exit from here. Okay, similarly, hot fluid will come over here, spread over the plate and exit from here. Okay, so what you can see over here is like when I'm considering two plates, these two plates are attached very close to each other, and how much thickness will be there between, or we can say how much opening will be there between two plates, that will depend on the thickness of this gasket. Okay, because once we place the gasket, they are very tightly attached to each other. Okay, if you observe this assembly, You cannot even see through the plate. These are so tightly placed. These plates are simply just to show how the functioning is done. Okay, so in between these two plate, only cold fluid will move. Okay, and in between these two plates, only hot fluid will move. I hope you are getting my point. So, how the heat transfer will occur between two plates? I'm having the cold fluid, and just uh, beside the what we can say, beside plates, we can have the hot fluid, and similarly we can have the assembly, like once I'm having cold fluid, then second hot fluid, then cold fluid, then hot fluid. So between this cold fluid and this hot fluid, the heat transfer will occur through this wall, through this plate. Okay. Therefore, therefore these plates works as a uh, works to separate the to keep the fluid separate, along with it will provide the wall to have the heat transfer between two fluids. I hope you are getting my point. So this is the whole functioning of this. The plates have flat or corrugated faces. If you see these plates, these have some grooves and some wavy type of structure that I'll show you in the next slide. So in that way, the purpose of these corrugation or these grooves are, when fluid is entering, it gets turbulence when it is flowing through this plate, and because of that turbulence, the more heat transfer you can observe. And therefore, if you compare the heat transfer coefficient for plate type heat exchanger and shell and tube heat exchanger, that heat transfer coefficient is very high in this plate type, in the same given heat transfer area. Okay, heat transfer area should not be changed. Okay, so in that way you can observe the more heat transfer area in less more heat transfer coefficient in less area. And if you see overall volume occupied by these type of heat exchanger, that is also comparatively very less when we consider shell and tube heat exchanger. So these plates serve as a heat transfer surface that we have already discussed. However, this type of plates are used extensively in food and beverage industries. um, if you observe this assembly, okay, if you observe this assembly, what you can see, that these assembly are so compact that cleaning is difficult. Okay, cleaning is difficult in this type of, when you need to clean this, you need to deassemble these like each plate, and each plate you need to clean. Okay, therefore the limitation of this type of heat exchanger is, we should consider comparatively clean fluid over here instead of more fouling tendency fluids. Okay, therefore these are used in food and beverage industry, where the contamination and fouling are less expected in comparison to other industries. Okay, so these are mostly used in food and beverage. Okay, otherwise if you need to place like heat transfer between air or gas, you can use this. Okay, but for fouling tendency liquid, it should be avoided. Okay, so this is a plate type heat exchanger. uh, if you observe in industry, you can see like this. Okay, so they are very compact. Okay, and what grooves and corrugation I was we were talking about in last slide, it is like this. Some type of wavy structure or some type of grooves are there, which increase the what we can say, between heat transfer between two fluids, and therefore heat transfer coefficients are higher for these type of heat exchanger. So this is a plate heat exchanger. Next, I am having the direct contact heat exchanger. If you have any query, you please ask in between, no problem. So, direct contact heat exchanger, when we are discussing these heat exchanger, hot and cold streams are come in contact without any separating wall, and therefore the meaning of direct contact heat exchanger will work. Okay, so what we can say, high rates of heat transfer are achieved. Okay, because there is no separating wall, and wherever I am having the separating wall, it will work as a hindrance to transfer the heat. Okay, it will give the resistance to transfer the heat, and that because of that resistance we observe lesser heat transfer coefficient. Okay, that you already know, where I'm having less heat transfer resistance, we can have more heat transfer coefficient. So here um, heat transfer rate are higher because of no separating wall. The equipment used is basically simple and cheap and is suitable for use with heavily fouling fluids and liquid where solids are involved, where solids are considered. Okay, so heavy fouling fluids means that uh, which have more fouling tendency. So wherever I'm having the heating surface or wherever I'm having the separating wall, fluid fouling will occur there only. So if I don't, and if fouling will be there, it will create another resistance to transfer the heat, right? So no fouling. If I don't have the separating wall, fouling or scaling will not be there. So heat transfer will be easier in that case. So direct contact heat transfer will be used for heavily fouling fluids and the fluid containing solid particles. The very common example of this is the water cooling towers. Okay, in industry, and you can have the air coolers in our houses also. So if you see the cooling tower, there what the purpose of this is to cool the air or to cool the gas. Okay, so if hot gases are used over here, and these hot gases will enter from the top, from the bottom of, obviously because of the usual movement of gases, it moves upward, so gas enters from the bottom, and the for heat exchange we consider colder fluid, okay, colder liquid. So that liquid will be sprayed over from the top, and heat transfer will occur over here. So colder gas will leave the this setup from the top. However, the hotter fluid, hotter liquid, not fluid, hotter liquid will be assembled at the bottom, and then it enters into this heat exchanger, where the temperature of this hot liquid will again, we need to bring to the normal temperature or cold temperature. So that will again happens in this heat exchanger, where it gives the heat to the colder fluid which is entering from here and exiting from here, and then its temperature will be cooled down, and then it recycles back to the tower. So in that way, direct contact heat exchanger will be used. Okay, so that is direct contact heat exchanger, that is water cooling tower. Next heat exchanger we are having is the air cooled heat exchanger. Okay, so once I'm having this air cooled heat exchanger, these units are used to cool and condense process streams with ambient temperature as cooling medium rather than the water. So when I'm considering air cooled heat exchanger, these are used in condensers, as a condensers, where where the cooling media is air instead of water. Okay, so when I'm having this air cooled heat exchanger, because air does not have the fouling tendency, okay, So this air cooling eliminates the fouling and corrosion problems associated with the cooling water, and there is no possibility of leakage and mixing of water with the process fluid. Okay, because this is used as a coolers or what we can say the cooling media, and as I have told you, it is more precisely, more specifically used as a condenser. So the like one fluid we can have like steam, you can consider that that needs to be condensed by giving its heat to air. Okay, so in that case there is no mixing of air with the gas. Okay, however, when we have this water and steam, there are possibility of leakages and mixing. Okay, so that you can observe over here also, but that possibility is comparatively very less in over here. So in this air cooled heat exchanger, maintenance costs are generally lower because of what we can say no fouling conditions. Okay. So if you consider this is the air coolers, and if you see these tubes, these are basically copper tubes, and these tubes contains the hotter fluid. Okay, and in this heat exchanger, the hot process fluid flowing through this tube bank of the fin tube. Okay, over here, above here, we have this fins which are basically just above this tube, but inside the tube there is no fin. Okay, so through this fin, ambient air flows, and that is blown across the tube by one or more axial flow fans, as you can see over here. Okay, so the point is when the what we can say blown over the across this tube, heat transfer will occur, and we can have hotter air from the below side. Okay, so these are air coolers. Now, another point I would like to tell you over here, that when we consider this type of fans, okay, and this fan is placed over the this over this fins, above this fins, okay, can I place this fan below side like here? Okay, instead of here, can I place this fan below side? Then also it will be able to suck the air. Okay, so heat transfer is possible in that case, there is no problem. Okay, and we can say that in both way it is possible. If I place that what we can say fan just above the fins or above the tubes, okay, this we can see, call as forced draft fan. Okay, I hope you are getting my point. Forced draft fan, and the what is the meaning of this forced draft? Because it forces the air to move in the system. What is my system? My system is this. Okay, where I'm having the tube banks as well as this fins. Okay, so when this fan is placed at the top, it blow or it throw air over this tube. Okay, it means it gives positive pressure in this system. Okay, therefore it is called as forced draft. Okay, however, if I place this fan below, okay, it will suck the air from the system. Please try and understand. If I place this fan below, okay, it will suck the air from the system. Okay, this is the system I already told you. Okay, so this because it sucks the air, it creates negative pressure in the system. Okay, therefore it is called as induced draft fan. Okay, once it placed over the top, it is called forced draft because it is throwing air to the system. Okay, however, when it is considered as induced draft, it will take the air from the system, creating negative pressure or vacuum over here, right? So in that way we can consider air cooled heat exchanger, but anyway you can place. There is no problem in like more electricity will be involved and all. That would be obviously difference will be there, but that would be marginal. Okay, so in both way you can place. And if you see the air cooler cooled heat exchanger at industrial scale, it is like this. Okay, so multiple what air coolers you can use. And if you observe over here you can see the copper tubes in which hot fluid will move. So fluid will be assembled will be available throughout the this distance, throughout the length. However, through this coolers, a certain section will be cooled, and through which we can observe cooling of the fluid throughout the length of the copper tubes. Okay, I hope you are getting my point. Okay, so this is a air cooled heat exchanger. And here I am having another type of heat exchanger, which is a storage type heat exchanger. Okay, that also we have discussed in classification. If you recall, regenerative type. Okay, so these are also regenerators. So storage type means we discussed yesterday also that it use some packaging or some matrix to store the heat. So if you see, this is the matrix where the heat could be stored. Okay, so what will happen, it also has four different nozzles, A, B, C, D, but at one time only two nozzle will be operated. If you see, this is the hot fluid. Okay, hot fluid will enter from here. At that time these two fluid will be closed, sorry, these two valves will be closed. Okay, so hot fluid will enter from here and it will come to these tubes, and through this tube 2 matrix it will transfer its heat. Okay, and then the hot fluid exit will occur from here. Okay, so in that case at one time only the hot fluid will inlet and that will exit, but cold fluid will not enter into this. Okay, so once this heat transfer will occur between hot fluid and matrix, hot fluid will exit from here, and at that time these two walls will be closed. Fine. Further, this valve will open and this valve will open, where cold fluid will enter, and it will come over here, and the heat transfer will occur between matrix and this cold fluid, and the hotter fluid will exit from here by taking the heat from the matrix. So in that way it is called regenerative type. Regeneration in the sense that every time the matrix can be heated up or can be cooled down, so that would be regenerative type, or we can say the storage type as well. Okay, so in that way we can have this storage type heat exchanger. So here we will cover a few heat exchanger which are commonly used in chemical process and their functioning we have discussed. So that is all about classification and different type of heat exchangers. And uh, just give me 2 minutes, huh? I will start, please. Just 2 minute break. So I'm sorry for the delay. Are you getting any sound from my side, from background?
Yes, ma'am,
Hello.
a little bit.
Is it disturbing?
Not that much, ma'am.
Okay, okay. So please let me know, huh? Because that.
A little bit disturbance, ma'am.
Uh-huh. Hello. Is it okay, or is it I need to, because that is the sound of AC. So will it be okay with that, or I need to stop that? Hello. I'm not able to get.
Yes, ma'am.
That sound is okay, or it is disturbing?
We can continue, ma'am.
Okay. Please let me know, huh, if you will face disturbance continuously. Otherwise, I think okay, let me know if you have any disturbance. Okay. So, in continuation to the design, before starting design of shell and tube heat exchanger, there are some important parameters which you should understand. Okay. So here we will cover a few basic design parameters, or some what we can say thumb rules, so that you can use these thumb rules uh, in designing. Okay. So, as far as the basic design parameter is concerned, if I ask you that what are the basic equation to you have studied in heat transfer? Okay, you must have you can tell very easily that when we consider the heat transfer, it is mostly based on only two equation. Okay, one is mcp/dt to calculate the heat of one of any stream. Secondly, the heat which is used for transferring, that is q is equal to ua delta t mean. Okay, that sound is much. Just a moment, I'll stop that. Yeah. When we consider the basic heat transfer equation, this is one of the basic equation. Q is equal to UA delta T mean. Okay, and that Q, how we obtain that Q? That is basically the heat content. Q is equal to mcp dt. Okay, so only that much amount of heat you can transfer to another fluid through this equation only, right? It is a basic equation. I'm not going to in detail about each parameter that you already know. My point to show this equation is different over here.
Excuse me,
Like,
ma'am.
sorry. Yeah,
Ma'am, are you showing your screen? It's not visible.
yes. Okay, okay. Just a moment, just a moment. Now, is it visible now?
Yes, ma'am.
Okay, okay. So if you see, this is the basic equation, and you all are aware of that. My point to show this equation is this is the only equation we will use in designing. Okay, but here other all or we can say each parameter will be discussed in different way, which will be considered in designing. Okay, q that you already you can know that mcp is the only amount of heat that you need to transfer. Fine. If I consider this overall heat transfer coefficient, okay, this overall heat transfer coefficient, uh, depending upon the parameters, that is also a fixed quantity. Okay, so another parameter I'm having is this LMTD, that is, sorry, delta T mean, that may be LMTD, that may be arithmetic, whatever. Okay, so here my purpose to show this equation is how these each parameter will be considered in designing. Okay, so first of all, we will focus on this U and then this delta T mean. If you fix these two, you can calculate area because this amount is already fixed. Okay, and once you have this area, you will start calculating other things, like if you already know the heat transfer area, then you will calculate that how much tube will be used to accommodate that area in a shell and tube heat exchanger, right? So I will first focus on U overall coefficient and then delta T mean. So when we consider overall heat transfer coefficient, this is a reciprocal of overall resistance to transfer the heat, which is the sum of several individual resistances. So uh, consider this overall heat transfer coefficient, the before that we should understand the overall resistances, and before overall resistances we should discuss individual resistances. Okay, so when we consider a shell and tube heat exchanger, you can consider that or you can visualize that with respect to double pipe heat exchanger. What will happen in double pipe? There is an inner pipe, right? And the outer pipe, and the heat transfer will occur uh, through outer surface and inner surface of inner pipe, not the outer pipe. Okay, outer surface of outer pipe, from there only heat loss will occur, but heat transfer will occur in inner surface and outer surface of inner pipe. Okay, I hope you are able to follow. So, when we consider a shell and tube heat exchanger, if I consider a single tube, okay, single tube, and shell side we are having a fluid, and inside the tube we are having another fluid. Okay, so how many resistances will be there? Okay, uh, because each fluid there are three zone. Okay, one zone is the shell side fluid, another zone will be a tube side fluid, and third zone will be the wall, right? But when I'm considering the fluid and considering the flow of fluid continuously, there is a formation of scaling at inner surface of the tube and outer surface of the tube, right? So then how many things are there? We have fluid, we have scaling at outer surface, we have the tube wall, we have scaling in inner surface, and we have the fluid in inside the tube. So total 5 parameters I am having, total 5 resistances I am having. How these resistances will be counted? If I consider outer surface of the tube, okay, one resistance will be by the what we can say, the fluid film, which which will occur over the scale. Okay, I hope you can understand that. Okay, if I consider the outer surface, there is a scaling what layer, and above this there is a film of the liquid. So that film will give one resistance, that scale will give one resistance, and then the tube wall will give one resistance. Okay, similarly at inner side, scale film will be there, and the film of the fluid will be there over the scale. Okay, inner side. Okay, so again inner side, because of the that scaling, one what we can say, because of that scaling, the resistance will be there, and because of the film, resistance will be there. So 5 resistances are there, and when we consider overall heat transfer coefficient, reciprocal of all these resistances will give the overall heat transfer coefficient. Okay, so if you see, this is the outer heat transfer surface, sorry, heat transfer coefficient of the film. This is the heat transfer coefficient of the, we can say, the dirt formation or scale formation. This is the what we can say, coefficient because of the uh, wall, because conductivity will be involved over here, and this is the what we can say, the resistance, sorry, this is the coefficient that can be observed by inner scale formation, and this is the coefficient which is formed by inner fluid. Okay, so because of that, overall heat transfer coefficient contains 5 different terms, and this equation you must have read in your heat transfer course. Okay, so how to derive all that, that I am not going into detail, assuming you already know this. How to apply that, that we will consider over here. So all these parameters or nomenclature you are already aware of. So how this HI and HO we can find out? It will it will depend on type of operation is going on. Okay, that we will see how to find this HI and H naught. How to find this HID and HOD, that will depend on the nature of the scale. Okay, and how to decide that, that we will discuss. And this thermal conductivity, this is this property of the material, we don't need to consider that again and again. Sorry, we don't need to consider that from any space for any, what we can say, any variation or so. This is the fixed quantity with respect to the material. Okay, so Kw you can obtain. How we will sorry, how we will find HI D HOD, that we will see, and HI and HO, that we will see. Okay, but you understand one thing, that HID and HOD, that you can obtain depending upon the fluid. Okay, from the standard table. I will show you after some slides. However, when you consider this HI and this HO, okay, this HI will depend on the what we can say, size of the tube. Okay, and size of the tube will depend on the heat transfer area. Okay, once you calculate the heat transfer area, you can decide the size of the tube, and you can calculate the total number of tubes which will be required to accommodate that heat transfer area. Okay, the point I am trying to emphasize on over here is that it will depend on the heat transfer area. Okay, and that heat transfer area will depend on this U. Okay, and you are already calculating this U over here. Okay, so the point is we need some initial value to find this U, to find out heat transfer area, and then to find out this Hi and H naught, then again to find out this U naught based on this equation, compare with the assumed value. The point over here is that this is hit and trial method. Okay, so hit and trial method will give you the initial overall heat transfer coefficient, some assumption you need to take. So how you can assume that? Okay, so it will depend on this overall heat transfer coefficient chart, which is this I have taken from Richardson Coulson volume 6. Okay, which is which is used for design purpose. So this is available, I think chapter 12 it is there, you can see. So if you see this chart, it has three different lines. One is for process fluid, okay. Process fluid coefficient, it means you need to calculate you need to consider the process, sorry, you need to consider the fluid which you need to either heat it up or cool down, okay. How you do this? This is the service fluid. Service fluid means which could be used as a utility, okay, to transfer to heat up, sorry, to heat up this fluid or to cool down this fluid. Okay, third line is the estimated overall coefficient. Okay, so how to consider that? Let's say I'm dealing with this, you can say heavy organics or any other fluid, because process fluid you already know. Okay, so the category you can already decide from this. Okay, so heavy organic, if I'm taking, the whole range vary from here to here. If you see, this is the whole range of the coefficient. Okay, of the coefficient variation. So this is the heavy organic. Cold or service fluid we can consider, let's say cooling tower water, so it is moving from here to here, or anything you can take. Okay, just for example I'm taking cooling tower which is varying from this to this. So how you need to decide the overall heat transfer coefficient initial value? Okay, if you know the fluid, just consider middle point of this fluid. Okay, if this is the middle point, and if I'm considering, let's say, heavy organic, middle point will be somewhere here. Okay, you join these 2 points through a straight line. Okay, join these 2 points through the straight line. Wherever it will cut this point, okay, this line, that value you can consider as estimated overall coefficient, or that we consider as the assumed value of overall heat transfer coefficient. Okay, based on this assumption we will calculate all equations or all parameters which we will discuss in subsequent slides. Okay, so I hope you understand how to find overall heat transfer coefficient assumed value, right? So any section you can take, just consider middle of that and middle of that, join these two lines, wherever it will cut this middle line, that you can consider as assumed value of heat transfer coefficient overall. Okay, so in this way you can decide U value, and in this U value you need to decide the dirt factor, you need to decide Hi and Ho value, all that. So dirt factor, how you can decide? This is uh, this is basically dirt factor is most process and service fluid will foul the heat transfer surface in an exchanger to a greater or lesser extent. The point is, whatever fluid you are considering, except the except the deionized or demineralized water, okay, where all what we can say, the fouling tendency content you have, you can remove. Okay, so otherwise all the fluids will have the tendency to scale the surface. So the deposited material will normally have relatively low thermal conductivity and will reduce the overall heat transfer coefficient. Okay, also if it reduces the heat transfer coefficient, the heat transfer area will increase. Okay, so it is therefore necessary to oversize an exchanger to allow for the reduction in performance during operation, because right now we are designing the heat transfer equipment, or let's say shell and tube heat exchanger. Okay, it means that heat exchanger is not existing. Okay, so how this fouling will come into the picture? Okay, because once I'm having the designing, I will manufacture the shell and tube heat exchanger, then operation will be performed. So during the operation, this type of situation will occur definitely. So we will consider that in the from the beginning, considering the desired heat transfer, or we can say desired dirt factor, you can increase the area. Okay, so that oversize of heat exchanger will depend on how much dirt we are considering. Okay, so fouling factors are difficult to predict and are usually based on past experience. Okay, just a moment. हेलो. हाँ हाँ हाँ, ठीक है ठीक है. So this selection of the dirt or fouling factor, it will be based on economic decision we need to make. Like optimum design will be obtained by balancing the extra capital cost of larger exchanger. Okay, actually, if I tell you, like more dirt factor you are considering, okay, lesser heat transfer coefficient you will obtain, right? More dirt factor, lesser heat transfer coefficient, and more heat transfer area. Okay, so it means larger heat transfer area you need to consider. Okay, larger heat transfer area means more capital investment you need to do. Okay, now if you are having larger heat transfer area, or what we can say more larger heat exchanger, there are possibility to have fouling or scale formation. What we can say, it will take longer time. Okay, longer time means longer time for cleaning you need to invest. Longer time of cleaning means operating cost will be less because of the, we can say, the cycle time to clean that would be larger. Okay, so larger heat exchanger will have more capital investment but less operating cost. So that is the perfect case for optimization. So once you consider the continuous plotting of the operating cost and capital investment with the increment in dirt factor, you can reach to at the optimum uh, dirt factor, where you can have the minimum total cost. Total cost means capital cost plus operating cost. Okay, so in that way you can decide the optimum value of dirt factor. Duplicate exchanger should be considered for severely fouling system. Because of the maintenance, heat exchanger operation will be stopped, and that can be continued in standby exchanger. In fact, that is not advisable for exchanger. That can be used for all equipment. We usually have one standby. Okay, and if you see this table, this is already in volume 6, Richardson Coulson volume 6. And according to the fluid, we can have dirt factors. Okay, and accordingly, we can have the coefficient. So HID, HOD, you can directly take from this table, depending upon the fluid. Okay, so this is about the dirt factor. Here I am stopping today's class. We will continue in next class. I'll discuss, I'll see when the next class will be there. Okay, so that's all from my side. If you have any observation, any query, you please ask. But that's all from my side. So thank you everyone for your patience. What happened?